So if we have executed the basic statistic test and decided that there's some potentially significant results in those means, then what do? We've decided we basically want to accept the accept the alternative hypothesis that the means are not all equal. And so that leaves us, well, where do we go since we can't conclude that they're all not equal? And so that's the whole thing here, is we need to do more to find out which means differ. And there's a lot of different ways out there to do this. We're going to just talk about two, one of which is a fuzzy-wuzzy way to do this, and another is a numerical way to take a look at it. But there are a lot of different approaches that have been put out into practice. Okay. The graphical comparison of the means is a very much a sort of a seat of the pants approach. It keeps in mind that under our null hypothesis, right, all the means were equal. Right, and that says something to us very important about that. If we pool all of the data together into one large data set, then we're going to expect that we're going to end up with, when we look at this grand mean, a normal distribution centered on the grand mean, right? And our estimate of our population standard deviation then can be given to us by the mean squared error divided by n, where n here is assuming that each subgroup has the same number of samples in it, right? This is not capital N, and there's the textbook will show how you can do this as an aggregate here if you have different, if Ni does not equal Nj. For us it does. So MSE over N for our specific case was 0.064 divided by 10, right? So 0.0064. Okay, and so then what I've done here is I've plotted a normal distribution that has the standard deviation given to us by this expression, but I've only plotted the distribution on 3 sigma on either side, right? So this plot from here to here is a total of 6 sigma, and really 6 sigma hat, right? And that should give us 99.7% of the population, right? And here's your aggregate data. And so now think, if you had that population, you were going to draw out of there randomly, out of that entire population, 10 values, right? And then you were to set that aside, or in a sense with replacement, but keep those numbers, right? Get an X bar, bam, there's one of our X bars. And then you do it again, and that is 10 more samples, and you do that again, right? And so we would expect, if these 3 different were pulled out of the same population, that it should be reasonably likely that these 3 are going to somehow then be pulled together and would be close enough to each other that this little guy here would embrace those, right? And so the idea, and I've just drawn this one in one particular location, but the idea is you can shift them around. And note, when we do this, that A and C are pretty far apart. Now, they're pretty far apart, but they're still under our 6 sigma band, and so, yeah, I don't know. These 2 are close together, right? I can shift this around, and they'll be right there close to under the body here, but if I shift this over to get down, then this one's going to go outside. Yeah, and that sort of is reflective of, remember, we had a p-value in our test statistic that was about 2%. And so we're not quite really far out there, but we are kind of. So all this does is it gives us a hint whether or not these three means really are about the same or not. And it suggests a little bit about maybe that these two, this would be B and C, are probably together, you think, maybe, and that this one's not. So let's go look at a numerical way that we can address this specific idea rather than just a sort of graphical approach. Okay, and this technique called the Fischer's least significant difference method was probably chosen by the authors because they use it in practice. Either that or they liked the symbols and they knew that would appeal to their audience. I don't know, right? Having a little fun here. So the LSD method here is going to have a null hypothesis that says that between just two of these levels or treatments, that the means are the same, but only two now. We're going to break this apart. And our test statistic is going to be t-distribution, so we're going to have t naught, and we'll have x bar, the sample mean for one, minus the sample mean of the other, all over the square root of twice of the mean squared error divided by lowercase n. Again, this is a lowercase n, not capital N, and not n sub I. If you have mixed, then that we have to adjust the formula a little bit. If ni does not equal nj, this assumes that it does. Right. So for our case here, square root of 2 MSE over n would equal square root of 2 times 0.064 divided by 10, and that's equal to 0.113. So that's our test statistic. Right now, the x bar values that we had were 1.721 for x1, x bar 2 was 1.487, and x bar 3 was 1.349. And let's rewrite that as A, B, and C. Okay, and so let's set up some comparisons here. Let's look at A compared to C, A compared to B, and B compared to C. Right, and the difference in the means, now let's just do an absolute value here, x bar I minus x bar j. Right, for A compared to C, right, so 1.721 minus 1.349 is 0.372. And for A to B, we've got 0.234, and for B to C, we'd have 0.138. Okay, now the t statistic associated with each one of those then, right, I'll call it Tij, is going to be 0.372 divided by 0.113, so that's 3.29, and then 2.07 and 1.22. We want to compare that to the test statistic. Right? Well, at least that's one way that we could do this. Right? And the test statistic then, our T alpha over 2 for two-sided, and then we have A times n minus 1 degrees of freedom here. So our A value, we had 3 different groups, right? And then n minus 1 would be 10 minus 1, so that's a 27 degree of freedom. Right, remember, that was the within sample degree of freedom that we had before. It turns out to be equal to that. Right? And so if you go look, for instance, at T 0.025 and 27 degrees of freedom, you'll get 2.052 as your test statistic. Right? And so if that's the case, then 3.29 is greater than 2.052, 2.07 is greater than, but it's not greater than down here. And what does that tell us? Well, it tells us that we should reject the null hypothesis for A to C, reject the null hypothesis at the 5% significance level for A to B, but do not reject for B to C. Right? And so let's go back up to what this says up here. A is sitting way out here. We're going to reject that A compared to C, right? We're going to say, no, those two are not the same. And at the 5% significance level, no, these two are not going to be the same either, right? So the only two that are the same, or I shouldn't say that, the only two that we don't have evidence that are different are then B and C. And that's another thing that people will do, is draw a line between those 2 points to indicate that the testing at this 5% level says that, yeah, those are about the same. Now, if we redo this for the 1% level, then we'll get a different answer, right? So, but now we have more detail than what we did before. We didn't know which one, and now we know it's A. That's the one that's sitting out there and is likely to be the one that's not equal to the others.